Hello, everyone. Welcome to our presentation. My name is Moreno.
My name is Alyssa Gallegos.
Nancy Rodriguez.
And I'm Diego Garza. And today we're going to be going over thermodynamics and how they play a role in heat pumps.
What are thermodynamics? The study of heat transfers and its relationship to the work done by the system. First law of thermodynamics. The change in internal energy of a system equals the net heat transfer into the system minus the net work done by the system. Relates to the conservation of energy principle. Changing U equals Q minus W. The changing U is change in internal energy, Q net heat transfer into system, W net work done by system. Second law of thermodynamics, heat transfer occurs spontaneously from higher to lower temperature bodies, but never spontaneously in the reverse direction. In a cyclical process, it is impossible to have a perfect conversion of heat transfer into work done. Changing U equals 0, so Q equals W, meaning W equals QH minus QC. Thermodynamics applications in daily life. Related to the second law of thermodynamics include refrigerators, air conditioners, and heat pumps.
Yes, the heat pump. When we're talking about thermodynamics and we're talking about the transferring of heat, the heat pump is a way that we're actually able to actually do this transfer of heat from one environment into the other. You'll see examples in the heater or an AC where a heat pump is able to take in heat energy, whether it be cold or hot. Cold or hot would still be considered heat. It's whether it's high heat or low heat, and transferring that into an indoor environment and then cycling it back into its own system in order to be cycled from cold air to hot air to cold air to hot air, depending on whether you're starting with cold air to hot air in the heater or hot air to cold air in an AC. And in this next slide, you kind of see the components of what makes up the heat pump. So here, first is a condenser, where actually I want to start off with the compressor, where first you see air that's taken in is essentially compressed into these coils, which then the condenser forces that compressed air into a liquid. From here, it goes into the expansion valve, which kind of regulates the amount of fluid that's going to go back into the system. And then from there, it goes to the evaporator, where it actually gathers the cold air, which can be considered the start, where it absorbs air into the heat pump. And then that air brings in heat energy, whether it be cold or hot. In this case, the example is a heater where it's taking in cold air and then transferring it out back as hot air. In the next slide, we have it a little bit broken down more into steps, where in the evaporator, the working fluid responsible for the heat transfer is turning the cold outdoor air into gas. From here, the compressor increases temperature and pressure of the gas, which then causes it to be forced into the condenser coils. And the condenser coils are heated. And then because the temperature of the gas is greater than the room temperature, that's where that heat transfer occurs. So all of a sudden, that heater is sending in a lot of hot air just because all that compressed air in those coils are getting heated. And then the gas condenses into a liquid, and then that heat transfer occurs. And then it goes back, and the fluid goes back into the expansion valve in order for it to be cooled down and then go back into the outdoor evaporator coils. And then from there, it gets cooled back down, and then it's cycled on a repeating system.
In this picture, it shows two scenarios where a heat pump is being used and how it works as a heater and an air conditioner. In the winter scenario, the cold air from the environment goes through the heat pump, which then transfers the air to become heated air. This heated air is then released into the environment of the home. Then the air from the environment of the home cools It goes back into the heat pump and is released into the outside environment as cooled air. In the summer scenario, the heated air from the outside environment goes through the heat pump and transfers into cooled air that is then released into the environment of the home. Once this air becomes warm, it is then cycled through the heat pump again and is then released into the outside environment as heated air. This process will keep going on and on until the heat pump is removed, cycling the air from the environment from hot to cold and from cold to hot. The equations behind it, QH equals QC plus W, W net equals QH minus QC, efficiency equals W divided by QH. QH is the heat transfer out of the hot reservoir. QC is the heat transfer into the cold reservoir. W is work. QH, QC, and W are positive with their directions being indicated on schematics. Efficiency is the fraction of heat that is converted into work, and the units are joules.
Okay, going over everything that we've just gone over, let's try an example. In this example, a coal-fired power station is a huge heat engine. It uses heat to transfer energy from burning coal to do work to turn turbines, which are then used to generate electricity. In a single day, a large coal power station transfers 2.5 times 10 to the 14th joules by heat from burning coal and transfers 1.48 by 10 to the 14th joules by heat into the environment. In this example, it's asking us two different things. What is the work being done by the power station, and what is the efficiency of the power station? Now, before we can even get into the efficiency of the power station, we need to handle that first part, because we don't even know how much work that we're dealing with in order to determine its efficiency. And this question isn't too hard. All it is just a simple plug-in into an equation. All you would need to do is identify your heat transfer out into the hot reservoir and the heat transfer into the cold reservoir. And as we can see from the heat from burning coal, that's your transfer out of the hot reservoir. So that Q of H is going to be 2.5. And then the transfer of heat into the cold reservoir, which is explained as heat into the environment, is going to be our 1.48. So we have our QH and our QC. From there, it's just plugging it in to get our work, where we just subtract our QC from our QH, and then from there we get the total network, network, which is 1.02 by 10 to the 14th joules. And now that we have that, we can find out the efficiency. And again, it's a simple plugin. You just need to know what you're working with. And since you already identified QH, all you have to do is plug in your W and your QH and divide W by QH to get the efficiency. So all you're doing is dividing 1.02 by 10 to the 14th joules by 2.5 by 10 to the 14th joules. And from there, you get your efficiency, which is 4.08 by 10 to the 27th. And then just to check your understanding, we're going to be answering these two questions. Now, if you remember from the beginning, what is the purpose of a heat pump? And then we just went over this right now, which equation represents the network done by a system in a cyclic process? I'll give you a second. Okay, let's see what it is. The purpose of a heat pump is that it uses work to transfer energy by heat from a cold environment to a warmer environment. Now, remember heat pump. Heat is actually making that air from that cold environment, extracting it and bringing it into a warm environment. It is similar to like an AC unit, but that would not be a heat pump. No. Remember, with heat, you're actually drawing in heat from somewhere that's not going to, and then from the equation that represents the network done by a system in a cyclic process, we just went over this. Your work is going to be your heat transferred out of the cold reservoir and subtract the heat transfer into the cold reservoir. The remainder is just going to be the total amount of work that happened throughout that whole heat pump process. And that should be it. Thank you so much for listening. I think we're good.